Good morning, mathematicians. We had an interesting question yesterday about asking what the analog of the Sylow theorems are in representation theory. And I don't know if we have such a thing, but I want to start exploring that in today's episode. So that's what we're going to do. Yeah. And I guess the first thing to say, well, the first thing to talk about is maybe what are the analogs of Lagrange's theorem? I mean, there's a lot of ways we can interpret this, right? There's a lot of ways we can interpret this. How I would interpret such a statement is, this is taking up everything. You learn the depths of a subject you just started. Well, good. Hello, Kostaka Corey. So, you just started representation theory, Locke? Oh yeah, I guess you were asking. Me about resources yesterday. So, one of the theorems that we're going to use. So first, let's talk about what are analogs of Lagrange's theorem. Well, we have a result that says. So let's work over just the complex numbers now. I was looking at a Keith Conrad paper, of course, that talked about how this fails in characteristic P, but let pi be a complex erep. Good morning, Arad. You're watching Math Research Spawn live. Kind of. I mean, I don't know. I don't know if there's, results here that people already know or to publish, but this is how it starts. Someone, good morning, Mom. I love you. And this is how it starts. Someone says something interesting, and then you start investigating it, and you think about the theorems that are already known, and then you start looking for other things that are known. So let pi be in complex irreducible representation of dimension d. Then d divides the index of the center. So this is, you could, in my view, I guess, again, there's lots of ways we can interpret, like, what should the Lagrange's theorem be? And, I guess in general you might think about all sub-representations. So I think a natural way to interpret it is about orders of the dimensions of representations, right? And so this is very much so Lagrange's type results should be restrictions on the orders. And then Sylow theorem type results should be on the existence of orders, right? I mean, we know that there's always the trivial representation. So we know that there's always an irreducible representation of degree 1. Homology or number theory, I wouldn't want to choose. I do what I do because I like them both. And besides, I mean, they're also interconnected, right? It's not like it's not like those are disparate things, like the proof of the Weil conjectures. That's like Atalco homology, but it's like a result in number theory. Or, I mean, you should see my other live stream. I have another series of live stream videos called where I teach myself Galois cohomology. That's literally the marriage of homology and number theory. Yes, Locke, this is representation theory. I mean, I made a statement about a representation, right? About a representation. So now let's see. There's also some sum of squares formula that we want here. Right. So we also have the following. We also have the following formula, right? The sum of squares has to be the order of the group of all the E-reps. I am a statement about representation theory. You just realized half the background of Monstrous Moonshine now. Dimensions of E-reps of monster group is a sentence you understand. Yeah, there you go. That's half the battle. Now you just need to understand coefficients of the J function. Fourier coefficients of the J function, right? What's the best tactic to study 48 hours in 28 hours? It's right here. You're looking at it. You believe the sum of squares also works for compact Lie groups. I believe that works as well. Yeah, so we have so in other words, if pi 1 hello Nikolai, if pi 1 up to pi n denotes all of the irreducible representations of some group G, and the di are their respective dimensions, then we know that the sum of squares has to be less than the order of the group. So, I mean, in general, this tells us in some sense that the dimensions of our E-reps are generally much smaller than the order of our group. So, right, it's kind of like a coarse upper bound, right? Can take half a day. What are you guys talking about in chat? Speed up to 0.86602c. Your Lorentz factor will be nearly 2 there. I'm working on it. Hey, now that's just mean, Leo. Now you're just being mean. Don't make me take your blue gear away. Okay, now how do we make progress? How do we make progress? So I believe I saw a result. I haven't read the proof, but so we all know, of course, all of us, everyone here in chat, that all of the E-reps of an abelian group. Oh yeah, so I guess the answer is kind of, there isn't a very good answer. The answer is kind of stupid for what should I say? Abelian groups, right? Because we have abelian groups of all orders, and of course every E-rep of an abelian group is one dimensional. So for abelian groups, I mean, so generally any hopes of a Sylow theorem for arbitrary groups is like completely dashed immediately, because it fails as hard as possible. Every abelian group only has one-dimensional E-reps. Interestingly, a result that I've heard of, though, is that every E-rep of G is one-dimensional if and only if G is abelian. Which is to say, conversely, if you knew that if you had a group, you didn't know if that group was abelian or not, and you found an irreducible two-dimensional representation, then you know that that group could not have been abelian. As long as our PDFs are online. What are we trying to do? Trying to invent Sylow theory for representations. ASMR bidirectional mic is crazy? What? Can you hear this? I'm saying. Yeah, loud and clear. Loud and clear, Leo. Yeah, but if Leo keeps saying rude things to me, like the order of that I'm much less than the order of the group, you know, privileges will be revoked. Okay. So so hopes are immediately dashed for a completely general Sylow type result. I do not have crash course videos on representation theory. Maybe I should make some. I've been saying maybe forever. I have so many video ideas and so little time. Doesn't group theory Sylow also become much simpler for abelian? Yes. Yeah, because I mean, well, we know what all finite abelian groups look like, right? And so as soon as you know what your group is, like, it's very easy to classify all the subgroups. But it doesn't become trivial, right? I mean, Sylow, I mean, you can say things that are much stronger than the Sylow theorems, right? Basically, you can come up with, for finite abelian groups, you can come up with subgroups of any order that divides it, right? So the whole thing is like Lagrange says a subgroup, if H is a subgroup, then H has to divide the order. And then the Sylow theorems are all about trying to create converses to that, and they can fail to quite an extent. However, there's for abelian groups, it is an if and only if, right? For every single divisor of the order of your abelian group, you can come up with a subgroup of that order. Is that true? Am I lying? No, I'm confident that's true. Yeah. And so the case for the representation theory version is kind of the exact opposite, right? It's like for subgroups of abelian groups, it's like, yeah, you have the converse theorem in full power. Not so much here. I mean, it's the complete opposite, right? For representations, it's like, no, you can't do it for any of the other divisors. What are all the EREPs of an abelian group? Are all P groups well understood? Like groups of order P to the N? I don't think so. I think it's too chaotic. Finite abelian groups are too boring? Nah, well, I don't know if I agree or not. Oh, you don't fully understand the normal Sylow theorems, other than converse. Yeah. Well, you gotta go study them. Maybe I'll make more videos on them at some point. I have like 2 videos on it. Lagrange needs to mind what he's saying. You don't know, but you would guess all P groups are well understood? I don't think so. Because like if you go look at like I was looking at tenacity, it didn't even say hi, and you're already saying bye. Like if you look at by the way, Keith Conrad has another document of like groups of order 16, and lately I was having to get my hands dirty with groups of order 32 and groups of order 64. I don't know if they fit into a nice pattern, to be honest. It's a bit of a chaotic, it's a bit of a chaotic zoo. So, yeah, I would be surprised if there's a nice classification, to be honest. Yeah, computing all extensions between p groups sounds somewhat tougher. Yeah, especially once the orders get larger and then you're doing like non-abelian extension. No, I mean, no, there's no way. There's no way. Does proofer P count as a P group? It is a spicy group. Isn't that like a pro P group? That's a thing that people study, right? Yeah. Ooh, enumerate all groups of order 2048? I don't think so. You don't think we've counted them all? Well, yeah, that's a big number, but how many groups of order 2048 are there? Wow. Oh, is not known. Yeah. And is strictly greater than this number. Wow. Oh, this is the number of groups with nilpotency class of 2. And the total number is expected to be much larger, though it will likely agree with this number in the first 3 digits. Yeah, that is crazy. Yeah. Yeah. So see, yeah, it's hopeless even for powers of 2. Well, you might say, hey, oh, hello, Christian. You might say, hey, 2 is always the prime, that's like, we shouldn't even call it prime because everything sucks for 2. But I don't think life gets easier for p to the n at all. Maybe I am a pro p group. Yeah. Yeah. You would think non-abelianness would add some hope to getting a converse. Yes. Okay. So actually, that's what I was gonna say, right? So what does this mean? So the if and only if is important here, right? Because this is sort of like a first step to a Lagrange's theorem. Because of the if and only if, we can say that if G is non-abelian, then there exists a an erep of dimension greater than 1. So we know now. So far, this doesn't allow us to say something about like the existence of a representation of a certain order, but this is a step towards that. Pro-P groups are a thing, and they have pro-Sylow theory. Yeah, I need to study that one day. I don't really know it well. Okay, then name that many. Have I taken any differential geometry courses? Yes, I've taken a course in differential geometry. Why do you ask? Let's also... Yeah, so here is also a paper I'm looking at for other reasons, for secret, possibly research-related reasons. There is this paper here, groups whose irreducible representations have degree at most 2. And so basically, well, there's also an extra condition. So not only is it representations of degree at most 2, well, here's a characterization. So this comes from a different paper, actually. But let G be a finite group and suppose that F is an algebraically closed field of characteristic greater than 2. I think there's a characteristic 0 version somewhere here. Yes, algebraically closed field characteristic different from 2. Yeah, so I think this is the characteristic 0 version. And then this is star stable. So basically all the ereps are like self-contragradient is the other condition. Is QZ isomorphic to Q? No way in hell. No, definitely not. There's an easy way to prove that. Think about orders of elements. Yeah, so here's a nice classification. So G is abelian, so already know those are all the one-dimensional ones. And so then, therefore, basically, any non-abelian group that fits into this classification is going to have a representation of index 2, right? Because these are representations that have degree at most 2, and if it's abelian, it has to have a representation of degree greater than 1. Therefore, these are going to be the groups that have a representation. So we could view this as a kind of Sylow theorem, if you like. So the only other options, if G contains an abelian subgroup of index 2, and so basically that means we have an extension. Contragradient is if you have a vector space, you take the dual space, and then if rho is a representation on V, then this induces a representation on the dual. Yeah, something like, well, you don't even need to, I mean, here we're doing finite groups, so we don't need to do smooth vectors. But you're right, Arad, definitely in the, infinite dimensional case, if we're talking about Lie groups and stuff, we gotta do it. So in this first case, what do we have? We have this group fits into some short exact sequence where, let me see here, of index 2, right? Where specifically the non-trivial element of C2 acts by sending elements of A. So some sort of like dihedral groups are like a special case of this. P with angry eyebrows, yeah. Yeah, he's mad because he's all turned around. So representation is self-contragradient if it's isomorphic to its dual rep. Yes, exactly. And there's, yeah. And what are the other possibilities? G contains index of order 2. So there could be, by the way, there's crossover between 2 and 3. So G is a subgroup of index 2, where A is an elementary abelian 2 group. But now there isn't any restriction on the action. So here we just have C2 to some power. And then what's the last one? You need more years to be here? That's not true, Yomo. That's not true. You're here now. You're soaking up the knowledge. These live streams are for everyone. Even though sometimes we get fancy and complicated with it. New word for me. You would have said self-dual. Yeah, I mean, maybe people probably say that as well. Contragradient sounds cooler. Yeah, I mean, it does make sense in the cases where where Rod was talking about smooth vectors. Like, you do need to do more stuff in like cases where you're dealing with like Lie groups and there's topological things to worry about. It's more different than just taking the literal dual space. There's more things to take care of. So maybe you could justify it like that. That's why there's more of a word. Yeah, but no, contragradient, self-dual, like these should mean the same things. Yeah, and then finally the center is an abelian 2 group of index 4. And so there's two possibilities, right? There's two possibilities. Either we could have C4 at the tail end, but that would mean that G mod the center is cyclic, which implies that G is abelian. So actually we can ignore that case because we already understand it. And then the other one would be this. So here we have the Klein 4 group, sometimes written as V4. With the additional information that this has to literally be equal to the center. And I believe that this actually implies that the action that you get of V4 on the center in terms of group the like group extensions is the trivial action. You can show that this implies that it acts trivially, which is nice because then we're not worried about all these complicated module structures. Actually, you know, like you can just go look up, oh, what's the second cohomology of V4 on an abelian group? Well, and we even know it's C2K specifically, so you can go look that up. Playing the lean natural number game on stream would go hard. Yes, that's true. Maybe I'll do it eventually. As I've said, I mean, I may do lean streams eventually. Anyways, if I got that postdoc in Sweden, you bet your butt I would be teaching myself lean on live stream. 100%. You feel like the context where we have Lie groups, why would anyone say dual to mean non-continuous dual? Yeah, I mean, sure. That's true. But is just continuous dual enough? Like, you need to take like the smooth vectors specifically, which has some particular meaning. So it's maybe not so straightforward. You think the last one feels oddly specific? I think they all feel oddly specific. C4 at the tail end would get you stopped by TSA. Indeed, Arad. Indeed. That's why we ignore it. Not just the continuous dual, exactly. I don't know if I like what you're saying to me, Leo. Yes, you need smoothness conditions. Well, I mean, definitely if you have a Lie group, right? You want things to be smooth, generally. Homology coming clutch, always. Wait, to spell contragradient? No. Is it? No way in hell. Really? I should know that. Seems gross. At least in the totally disconnected case. Yes. Totally disconnected case is different. Of course, that's the one I'm most used to. And there we have, there we have fixed by open subgroup. Yeah. Okay, so what do we have? So we have what is this? So you know, in the special cases, from some papers, we have certain conditions to force E-reps of degree 2. Nice. Okay. Now, what else? What else could we do? So there is also the process of constructing irreducible representations of semi-direct products, a la Sarah's book. Could GAP calculate the cohomology group for us? Maybe. I actually did. I think I showed you guys this on stream already. But I just, Sage didn't have, maybe I'm wrong, but I didn't see like nice things in Sage about computing cohomology groups. So I just computed things by hand. Yeah, so to explain some of this code. So here, I even defined the Klein 4 group by hand, because I wanted to work with elements as lists. And then basically, you see here I had code that created cocycles. So I had functions representing the cocycles. And then I weeded out those to take normalized cocycles. And then so you can see here, yeah, so let me run some of this code actually. Is there a reasonable case where someone would say contragradient and dual to mean different things? Well, I mean, it's definitely, it's believable to me that you would maybe want to, if you're doing some stuff, you might want to consider the dual vector space, right? Just as a thing onto its own, right? As opposed to the contragradient representation. I'm just kind of guessing here. I don't know if there's a Sage package that compute. I didn't see anything that looked, and honestly, to me, it was just like, well, it's just easier to write my own code from scratch. Well, they had code for spectral sequence computations? That's wild. Well, spectral sequences should converge in finite a number of pages. I mean, all a bunch of these examples we looked at like converged on the second page, right? Contragradient. Google says contragradient? No way. Contragradient representation. Contragradient, huh? Wow. I can't believe I never noticed that. I just said contragradient all the time. I've read this word a million times in my own work. Crazy. Crazy how I never noticed that. Yeah, so like, look, you can see I like defined even things to be the right. So I programmed like the normalized image. Oh, a bunch of code didn't even run. There we go. Right, and so I have here, like, you can see what this code is doing. It accounts for modding out by the co-boundaries. So I take these for f in n co-cycles, and then basically I'm like, okay, append, add f to this list, unless it can be written in terms of something, unless you can find it, that f, you can find something in the image to like. Its difference like lies in the image or whatever. Yeah. So, anywho, and then you could go. One could go. I didn't go here further, but I was thinking about I could define the group law on here as well, and then. Like I could easily maybe even it'd be a good idea to like define a class and take a group, whatever. I don't know if I don't think it's a typo. An example? Leo, you want an example of what? Of when a contragradient representation comes up? Do you have a totally disconnected vector space group? The group, I mean, in the p-adic case, your non-Archimedean group, you have, well, generally, so there's subtleties going on here. I mean, you have some p-adic group, and you have a representation of that p-adic group. And it is said to be smooth if the stabilizer of every vector is an open subgroup for all vectors. That's all it means. And so, so here this is like some totally disconnected group, right? It's like GLN QP. And your vector space V, I mean, this is a complex vector space. The way I normally think about it, I deal with complex vector spaces. And the thing is just the topologies between these two things are kind of incompatible. And actually, so I do think there is a perspective in which, so you could just take this as a definition and be happy with it. There's another thing you could do, though. There's like an operator theory approach where you actually equip this with the discrete topology. And then there's some way in which you're like, well, I take like a continuous map, or not quite continuous. See, I don't even know. It's like I take it into some sort of space of operators on here with the discrete topology, and I don't even remember the approach exactly. Contragradient is better than linear dual in this case. Yeah. Contragradient is exact on admissible representations. Right. Yeah. Yeah, and we also want we want contragradient to be double contragradient to be naturally isomorphic to the original representation, right? Who comes up with this? You're happy with homotopy instead? Why not have it all? You just realized you never asked yourself what the universal property of a semidirect product is. I think that came up. I think we were looking that up on stream. I don't remember exactly. Doesn't really have a nice one. I thought we saw some blog that when we looked it up before. Rep theory research. Your last year undergrad who likes rep theory. Hell yeah. But not so much topology. Wow. I mean, there's plenty to be done in... there's still stuff to be done in representation theory of finite groups, but I hope you can find space in your heart for topology, because these things all come together. And besides, Boris, homotopy theory, modern day representation theory is some like equivalence of right? The like Schulze whatever school of thought is like you're looking at the derived category on Bungie, which is actually like the infinity category, the infinity category version of the derived category of quasi-coherent sheaves on Bungie. And so infinity categories, you're basically doing homotopy theory. In Bungie, this is like some stock of G bundles. That's deep in homotopy theory. So these things go together. You just joined. These are different to regular Sylow theorems. How do you search for them? Well, there is no such thing as them yet. That's the sort of the point of the stream. One of my regular viewers yesterday asked, "Hey, what's the analog of the Sylow theorems in representation theory?" And I don't really know. There isn't really such a thing that's known. And so we're off on a tangent right now, but what I was explaining earlier in the stream, don't worry, the recording will be available, is, what should the analog of Sylow's theorems be in representation theory? And so we're kind of coming up with it right now, and I've listed some theorems that can kind of be thought of as analogs. So we're working towards it. Are double contragradients always the original? They should be, yes. If we're talking about like representations of p-adic groups, and if we're assuming our representations are admissible, but smooth and irreducible always implies admissible. Practical English question is then, if you use the word contragradient and use the word dual, will rep theory people think you're talking about different things? Probably not. They'll probably know what you're talking about. Why use big word when small word do trick? I don't know. Small is too many letters for what it means, right? 5 letters? That's pushing it. Yeah, that's enough, Leo. You're really gunning to get that gear removed. Sorry, could I repeat that? Oh, Daysen, welcome. Yeah, this is all investigation based off your question. I know you're scared of what you signed up for after hearing infinity, category, and rep theory. I mean, you don't have to. You could live your entire life. You could have a long, successful, fruitful career, an impressive career in representation theory, and never learn what an infinity category is. You absolutely don't have to. But there are places where these things naturally go together, and it is part of the modern toolkit. So. Yeah, fair enough. Okay, fair enough. Yeah, it's a stretch to call it homotopy theory, but hey, I mean, covering spaces of Lie groups also matters, and there's fundamental groups coming up there in the covering spaces matters in the representation theory. So, many successful pure mathematicians don't know what an adjoint functor is. That's true. Is it something you can briefly explain it? Wait, what is something I can briefly explain it? What are you asking about? Okay, let's see. But getting back to the task at hand here, I mean, go ahead, ask your question, Dason, what it is you want me to explain. But I think we can say some things about converse theorems for semi-direct products. Because what's the process of coming up with representations of semi-direct products? Well, we look at G acting on the set of characters. Oh, the Schulze school of thought? No, I can't explain it. Briefly explain. I explained. I explained it already. I mean, yeah. I don't know. I guess vaguely, representations are like representations on like Lie groups are like vector bundles, and so it's you think about Bungie instead of like a category of representations, I guess. And then you don't get equivalences of categories at the level of the honest to God categories, and so you go to the derived level. It's a natural thing to do. It's a weakening of equivalence. That's the best I've got. Adjoints are just homotopy equivalent of the underlying nerve? Huh? You're sure all mathematicians would understand them in 2 minutes? Yeah. Well, I don't know. Would some specialist in partial differential equations who's never had any use for the word category, it might take them, okay, you could probably explain the definition to them, but to have them internalize the usefulness, that's going to be harder, right, if it's not relevant to them. Sticking around in goo. Abelian group kills Sylow theorem. One random paper gives Sylow theorem for D equals 2. Well, it doesn't even. It's D equals 2 for only certain classes of groups, right? And so how do we build representations of semi-direct products? Well, we look at this action. We break this into orbits. Basically, choose some character chi of A, and you look at the stabilizer. So maybe let G chi is like the stabilizer of chi under this action. And then what do? Then we take, what is it, an E-rep of G chi? We take an E-rep of G chi, I think. And we lift it to, basically we have like the semi-direct product generated here, and we lift we lift row to here, which is just row AG defined to be row G, and we lift chi in a similar way, and then we induce this rather. We induce here this tensor product. And this will give us all of the irreducible representations. So, PDE people are like aliens. They don't count. Hey, Boris, we won't stand for this slander here. I used to be a slanderous little man like you, but then I grew up and I found love in my heart for PDEs and PDE people. So, you know a famous algebraic geometer who barely knows what an adjoint functor is. That is more surprising. But I guess, yeah, you can still do a lot of classical algebraic geometry. And there's like computational algebraic geometry, which, yeah, I could imagine adjoint functors wouldn't necessarily matter so much to you. Now, did I do this right? Actually, I have Sarah right here. Let me double check. I think it's around page 60. PDE people are the ones who bring in the money to the department. Yeah, exactly. Yeah, so if you like studying pure math, better shut your mouth, because it's the PDE people who, are the reason why math departments even exist. So think about that, yo. Let's see. Did I do this right? Character of degree 1. Yes. Wait, canonical projection. Yes. Right, that should be it. Yeah. So, that is quite the induced representation on semi-direct product, yes. But here's the point. This should be irreducible. LOL, you're a probabilist, or you're in probability theory. Your PhD is in spin glass theory? What? What is spin glass theory? What? Spin glass theory. The hell is that? Condensed matter physics. Oh, interesting. Describes a disordered magnetic state where magnetic moments freeze in random orientations below a certain temperature. Huh. That's cool. That seems fun. Do you spin glass in your free time? Good question. But anyways, the punchline is, so now this is an irreducible representation, and it should have dimension equal to the index, which should just be equal to the index of g chi in G, if I'm not mistaken. And so therefore, this is still, this doesn't say anything like, oh, it guarantees these kinds of groups have, it's like not a uniform kind of statement where you're like, oh, some prime P, whatever. But in these cases, it's easy to say, easy takes a bit of work and it really is context dependent. But this gives you a complete classification of, all the irreps that show up, and so in particular all of the orders, right? So, yeah, I don't know. That's a partial. Is kind of a Sylow theorem in a sense for semi-direct products by an abelian group. The index is always related to the dimension of the rep. Mysterious reasons for you. Maybe I could be doing something slightly wrong here, but yes, because I maybe made a boo boo, but generally speaking, like what is this induced representation? What is this induced representation? It's if v rho is the representation, because chi is a character, it's going to be the space of all functions from a semi-direct G into V, such that f of AG times BH is equal, f of this product, where the AG, so this is for all BH in here, and this is for all AG in the subgroup, is equal to, chi A rho G FBH, right? And so what does that mean? As a rough heuristic, I guess I'm jumping ahead with heuristics here. I don't have a formal proof, but if you think about the induced representation, so just take H some subgroup of a group G, then the induced representation of say the trivial representation in this case is just going to be all complex valued functions, which are left invariant under cosets, left invariant under translations by H, which essentially means that you can identify it, like it determines a function on the left coset. And so basically this will have a basis of functions being the indicator functions for the different cosets. And so you can see in this case that that the dimension will just be the index of H. So actually, yeah, I lied to you a little bit. I don't actually know 100% sure. I haven't thought about that the dimension of this space really will be this index. But I think one can say it will. Maybe we can also pass through the fact that it is a tensor product on the level of modules. So maybe we can use that. Is induced representation related to induced modules from Galois cohomology? Kind of, right? Yeah, I mean, through this equivalence of categories, you do have like a tensor product thing. You wanted to look up stuff on induced modules. You always found induced representations come up. Not the thing I wanted. Representation of groups R modules on their group algebras, yes. An induction coincides in these situations, yeah. So you're learning representation theory while learning Galois cohomology? Kind of. For any field, the representations of your category on k vector spaces is equivalent to modules over the group algebra of K, as Arad said. So really, representation theory of finite groups is just a special case of the study of modules. And what a Galois cohomology is cohomology, and it's basically also a study of modules. So really, it's like there's the study of categories of modules, and rep theory and Galois cohomology are offshoots of this, but then also like have some intersection, whatever. Isn't also like the weird other adjoint to Hom? Yes, induction's adjoint to restriction. Yes, I think for finite groups it's left and right adjoint. The left adjoint is given by tensoring with something, and the right adjoint is given with humming. Yeah, so this is the... I think I have an old video called Adjunction Junction, where I don't prove it, but I do at least state that we have this triple adjunction. If f goes from A to B, then we have this triple adjunction of functors. God, I always forget the order to write things in. The middle's restriction. I probably have this backwards. It's something like this. So like this is restriction of scalars, this is extension of scalars, and then this is extension of scalars. Anywho, I gotta, get to work doing actual work things. Actually, maybe I should carb up and go for a long jog. Maybe that's what I should do. Carb up, do some work while I ingest. Always forget left versus right. Yeah, I just look it up. It doesn't matter. I don't need to remember it. Okay, anyways. Thank you all for joining me. And I suppose tomorrow maybe we'll continue on this quest for Sylow theorems of